Hello again. This is Math 2232 coming to you from the College Uta page. The title of this lecture is Applications of Series. As always, please be an attentive learner while watching these videos. Now that we know how to represent functions as power series, we can begin talking about some more applications. Now, many of the applications that exist are beyond the scope of this course. You will encounter them in future math courses. It's why you take Calculus 2 first, and why Calculus 2 is a prerequisite for those courses. One application of power series is in the field of ordinary differential equations when you're finding series solutions, which is kind of the gold standard for solving many important differential equations. And so I plan to have a short enrichment lecture dealing with this next week. Another application arises in the study of partial differential equations, and there we use Fourier series. And again, I plan to have a enrichment lecture on this, at least opening the door to this. Many of the applications of series, especially those in these fields, rely on the fact that the functions can be represented as a series. In such applications, it is often difficult, if not impossible, to find the function itself. However, there are methods for determining a series representation for the unknown function and approximate it to any degree of accuracy. This is very powerful and useful, especially for engineering students. So let's begin with an example where we're to determine a Taylor series about x equals 0 for the following integral. Now this is the integral from, actually it's an indefinite integral of sine x over x dx. And again, this is something that is worth reviewing and also trying it to start with so you can appreciate the solution better. Now this is a function that does not have an elementary antiderivative. You could spend the rest of your life trying to find a u substitution that will work on this, but there are no u substitutions because there is no function whose derivative is sine x over x. So what we're going to do then is we're going to look at the integrand, which is sine x over x, and we're going to represent this as, here's the 1 over x. So we're stripping that out as a factor. But then what we're writing here is the infinite series that represents sine x. And so this, as you know from previous lectures, is the summation n equals 0 to infinity. This is minus 1 to the n. These are the odd powers. This is x to the 2n plus 1 all over 2n plus 1 whole factorial. But then we're going to take this x and we're going to distribute throughout, because we can treat this, and we prove these properties, that you can treat this as an algebra situation. This is kind of an infinite polynomial, and so you can divide all the way through by x. So we're going to do that. So instead of the power being x to the 2n plus 1, the power is going to be x to the 2n, and so this is what we have. But now we can look at this integral, and we can say, oh, integrating this is the same thing as integrating the infinite series, and we can do that term by term. And so we will move the integral inside, and when we move the integral inside, both the sum and we integrate each term. So what you're going to do is add 1 to the exponent, that is 2n plus 1. And you're going to divide by the new exponent, which is 2n plus 1. And we already have the minus 1 and the 2n plus 1 factorial there. And we will add a general constant of integration. So while we can't integrate this function in terms of known functions, we can come up with a series representation for this, and we have ways of estimating this series to any degree of accuracy. So you see, from a numerical engineering standpoint, we can solve a problem we couldn't solve before by means of infinite series. Now this idea of deriving a series representation for a function instead of trying to find the function itself is used quite often in several fields. In fact, there are some fields where this is one of the main ideas used, and without this idea it would be very difficult to accomplish anything in those fields. Our next example is an application of partial sums. And in fact, we've already seen this application in an earlier lecture. In the lecture where we were estimating the value of a series, we used a partial sum to estimate the value of the series, and we could get our hands around, at least in several important cases, our error, ERR-OR term. Now we can do the same thing with power series and series representation of functions. Now the main difference is that now we will be using the partial sum to approximate a function instead of having a single value as we had in the earlier lecture. So we will look at Taylor series in our example, and these are polynomials. And so we recall that the nth degree Taylor polynomial is given by, you just take the infinite series up to n, and this is the Taylor series. So t sub n of x means you go from I equals 0 to n, and these are the Taylor coefficients, and this is the Taylor series about the point A. So what we're going to do is we're going to use these Taylor polynomials to approximate the function itself. And so let's take a look at this. So this example, and again, this is a wonderful one for you to concentrate on both now, before, as we're going through this, just so you appreciate the solution more, or as you're reviewing for the final exam, this is something that's useful. So for the function f of x equal cosine x, we're going to plot the functions, and the function itself is y equals f of x equal cosine x, as well as the Taylor polynomials 2, 4, and 8. And we're going to plot them on the interval from -4 to 4. Now let's figure out what are these things that we're going to be plotting. So the general formula for the Taylor series is, and you remember that about the cosine, this is one that you committed to memory, so we just get the even powers, and so going up to the point 2n, so this is t sub 2n of x, is equal to, we have the summation I equal 0 to n, this is -1 to the I, x to the 2i, because these are only the even terms, all over 2i whole factorial. So the three Taylor polynomials that we got then are, this is t2, and notice that it goes up to x squared. t4 goes up to x squared, but it does include, excuse me, t4 goes up to x to the 4th, but it does have lower order terms, and t8 goes up, and it has, again, lower order terms of x to the 6th, x to the 4th, and x squared. I encourage you to verify these calculations. This is important practice, and I have asked questions for students to do similar kinds of things on exams, so it is worth your while to practice. Let's look at the graphs of these Taylor polynomials instead of the numbers this time, and we're going to compare them to the graphs of the cosine. Okay, so now you can see from the graph that the cosine is the red curve. T4 is shown in green, T2 is shown in blue, and T8 is shown in, I don't know if that's light blue, I don't know what that is, but that's T8. And so as you can see from these graphs that they actually do hug the function. They are very good approximation for the functions, and the higher we get, as we go from 2 to 4 to 8, we get better and better fit to the function. Now eventually all of these fall off as you get farther away, as you would expect, but often what we're doing is we're picking our points, like here we're expanding about 0, saying, well, we're really interested in what's happening near there anyway. So as you can see from the graph, we increase the degree of the Taylor polynomial. It starts to look more and more like the function itself. In fact, by the time we get to T8, the only difference is at the endpoints over here. So a very good approximation indeed. Also, the larger the interval, the higher degree polynomial, we get a good approximation for the whole interval. Okay, so before moving on, let's write down some more Taylor polynomials from that example. I think actually, we're taking T3, T5, and T9. Now notice that since we just pick up the even powers in this, we're not really changing when we increase the the index of these sequences by 1. So this is the same thing as T2, this is the same thing as T5, this is the same thing as T9. Now these are identical to what we used in the example, but it's not always the case. But the point to note that the nth degree Taylor polynomial actually has degree terms that are less than n, and in fact it could be 9 and you don't have a t to the 9. It'll never be more than n, but it can be less than n. Here's another problem, and again this is similar to problems that I have asked in the past on assessments. Find the first 3 non-zero terms. So that means if a term is 0, you don't list it, you list 3 non-zero terms in the Taylor series 4, and this is y equals f of x equal e to the x cosine x, and we're expanding this about 0. And again, there's benefit in giving this a go yourself, and also circling back and studying this example as you're preparing for the final. Well, you see, we're taking e to the x times cosine x, so we know that e to the x times cosine x, this is the Taylor series about 0 for e to the x. It's the summation in going from 0 to infinity of, this is x to the n over n factorial. And then we're multiplying that by the cosine, and this, again, is the cosine Taylor series. N equals 0 to infinity. This is minus 1 to the n. This is x to the 2n, and this is all over 2n whole factorial. Now, we don't have to completely multiply out these series, but we have to think about how this will happen. And so we're going through enough of these steps of the multiplication to get the to get an answer. Now the problem statement says we want to get the first 3 non-zero terms. That non-zero bit is important because it's possible that some of these terms will be 0. And when you're multiplying through, you see you're taking powers of x to the n times powers of x to the 2n. So some of these will be odd numbers, all of these will be even numbers, and so we really want to just get the ones that are non-zero. If none of the terms are 0, this would mean the first 3 non-zero terms would be the constant term, x term, and x squared term, because that's what we would get in a power series or Taylor series for this. However, some might be 0, and so let's assume that we'll get all the terms through x to the 4th. We'll have enough to get the answer. So we're taking this up to x to the 4th and this up to x to the 4th, and we're going to multiply and see what happens. Now, if we guessed wrong, it'll be very easy to fix, so we'll just extend to more terms. So let's write down the first few terms. We go up through x to the 4th in this one, e to the x. So we get 1 plus x squared by 2 plus x cubed over 6 plus x to the 4th over 24 plus dot, dot, dot. And here we get 1 minus x squared over 2 plus x squared over 4 plus dot, dot, dot. So now what we have is we have up to x to the 4th, and we'll see what happened. Now note, we do need to acknowledge that these series don't stop. That's why we put dot, dot, dot. But just for a second, let's suppose that each of these did stop, and we say, what will we get if we multiplied this out? Now, if this were the case, we would take every term in the second and multiply it by every term in the first. In other words, we would multiply first every term in the second by 1, then every term in the second by x, then by x squared, and so on and so forth. That's the distributive property. That's the way you multiply polynomials. Now, each of the terms that we neglected to write down have an exponent of at least 5, so multiplying by 1 or any other power will result in an exponent that is at a minimum of 5. And so we're going to be ignoring those. We'll see if we need them when we do the calculation. So let's start the multiplication process. Okay, so we start multiplying. This was when we took the second series times 1, and I realized that's an infinite series. This is what, so that's 1 times this. And then we're going to take the second series times x, and we get these values. Again, these are infinite series. This is going to be the second series times x squared over 2. This is going to be the second series times x cubed over 6, and 6 of course is 3 factorial. And this is the second series times x to the fourth over 24, and 24 is going to be 4 factorial. So we're multiplying through, and we get these. Now we're going to collect like terms. So we're going to take every term that has x in it, and there are terms that have x in it because there's one. And we'll collect terms, and we're ignoring anything that has an exponent of 5 or more, since we don't need those terms for this. So doing that, we will get, and you should verify this calculation, 1 plus x, this is x squared. And notice that those coefficients are going to drop out. X cubed, they're not going to drop out. This is x to the fourth, and those aren't going to drop out either, plus dot dot dot. So these are, when we collect all of these terms, we get that this is 1 plus x minus x cubed over 3 minus x to the fourth over 6 plus dot dot dot. Now there are the first 4 non-zero terms. So we ended up with 4 non-zero terms, and the problem said we wanted 3, so the answer to the problem really is just going to be the 3, but that's okay. If we had underguessed, we would have known we didn't have everything we need here, and we would have to go back and add some terms. So we don't have to completely redo the work, but our guess was good this time through. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.